Well, in the previous lecture, we had defined the linear functions and the dual spaces. And we had also done a theorem that relates the ordered base of a vector space with a dual basis. So let's recall that statement. The statement of the theorem was like this. So we were given an ordered base of a vector space V. If V1 through Vn is an ordered basis of a vector space V over a field F, then the linear functionals, F1 to Fn such that Fi of Vg, this is equal to delta Ig, where this delta Ig is the Kronecker delta function, and this is defined to be equal to 1 if I is equal to J, and this is defined to be 0 if I is not equal to J. Then the linear functionals these form a basis. Form a basis of dual of V, that is V star. And we had done the proof in the previous lecture, but for now, in this lecture, we will take examples where we will evaluate the dual basis once we are given a basis. So let's take an example number 1. Let this beta equal to, suppose V1, V2, V3. Let's choose these vectors from R3. So let the vectors be 1, 2, 1, 1, 0, 1, and 1, minus 1, 0. So let this be the ordered basis of R3. Then our question is, find the dual basis. Find the dual basis beta star. And then later on what we will do, also find beta from beta star. So first we will evaluate what is this beta star, the dual basis. Then once we are given this basis beta, we will evaluate the beta star. Then later on, since we will have found out this beta star, then from that beta star, we will assume that beta star is given and we will evaluate beta. Okay, now let's start the solution. And we will do the solution of this exercise by just using this theorem and this definition of the linear functionals, which are defined on these vectors of the ordered basis as Fi of Vj is equal to delta Ij. So by definition, so let beta star be the set of linear functionals F1, F2, F3. Then since we are actually here trying to define out the dual basis of R3, and since we know that the dual and the vector space itself has same dimension, now R3 has dimension 3 and this forms the basis. So the dual basis will also contain 3 vectors, and because the dual vector space also has dimension equal to 3. Let beta star be the dual basis. With the dual basis. Then by this definition of these linear functionals, so then this Fi of Vg will be equal to delta ig. So that is what we will get. We will get f1 of v1 is equal to 0, f1 of v2, sorry, f1 of v1 is equal to 1. This is equal to 1, and f1 of v2 is 0. And similarly, f1 of v3, this will be equal to 0. So this will be the how this linear functional of f1 can be obtained. Now similarly, f2 will have these properties. f2 of v1 will be 0, f2 of v2 that is equal to 1, and f2 of v3 that will again be equal to 0. And similarly, the linear function of f3 will have these properties. f3 of v1 is 0, f3 of v2 that will again be 0, and f3 of v3 that will be equal to 1. Because we have that fi of vi is 1, otherwise fi of vj is equal to 0 whenever I is not equal to j. So this is f3 of v3, this will be equal to 1. Now from these equations, we can exactly find out what is this f1, what is this f2, and what is this f3. So now let us do them one by one. So now f1 of v1, this is equal to 1, f1 of v2, this is equal to 0, and f1 of v3, this again equal to 0. Now this f1 is a linear functional, where f1 is a linear functional, on R3. Now, since we have in the previous lecture studied what is the how do these linear functions look like on Rn? So thus f1 of x, thus f1 of x, y, z will have this kind of a shape. It will be of the form ax plus by plus cz. And similarly, in fact, f2 of xyz will be of the form ax plus by plus cz, and f3 of xyz will be of this form ax plus by plus cz. So now let's evaluate this f1 of v1. Now v1 is equal to 1 to 1. So therefore we evaluate now. So therefore this gives f1 of 1 to 1. Now x is equal to 1, so this is equal to a plus 2b plus c. Now similarly, f1 of v2. Now what's our v2? Our v2 is equal to 101. f1 of v2 is f1 of 101. That's equal to a plus c. And similarly, f1 of v3, and our v3 is 1 minus 1 0. So it is 1 minus 1 0, and this one is equal to a minus b. Now by definition, f1 of v1 that is equal to 1. Now this one is equal to 0, and this one is also equal to 0. Now from this equation we will get a is equal to b. So this equation gives a is equal to b, and this equation gives a is equal to minus c. So these two equations in combine give us that a is equal to b, so this gives us a is equal to b is equal to minus c. So we can obtain the values from here now. Now if we put a equal to b equal to minus c in this equation, so then from first, so let's call this as equation number 1. So then from 1, then from first, we put a is equal to a, and we put b is equal to a, then it is 2a, and we put c is equal to minus a. This is equal to 1. So this implies us a is equal to 1 by 2. So thus, we have the values of a, b, c. So thus this triplet a, b, c can be obtained from this equation now, since a is equal to 1 by 2, A is equal to B, that means B is also equal to 1 by 2, and A is equal to minus C means C is equal to minus 1 by 2. So therefore, this F1 of X, Y, Z. So therefore, this is equal to X by 2 plus Y by 2 minus Z by 2. And this is obtained from this equation now because we have Ax plus By plus Cz. Now substituting A is equal to 1 by 2, B equal to 1 by 2, and C equal to minus 1 by 2, we obtain F1 of X by Z is equal to X by 2 plus Y by 2 minus Z by 2. So this is the first linear function. This is the first element in the ordered basis, beta star. Now accordingly, we can evaluate the second element now. Now again, by definition, we have F2 of V1. Now this will be 0. F2 of V2. Now this is equal to 1. And F2 of V3. This is also equal to 0. Now F2 of V1 means F2 of 1, 2, 1. Now again, F2 has the form Ax plus By plus Cz. So this is A plus 2B plus C. And F2 of 1, 0, 1, which is our V2. So this will be equal to A plus C. And similarly, F2 of 1, minus 1, 0. And this is equal to A minus B. But now F2 of V1, that is equal to 0. F2 of V2 is 1. And F2 of V3 is again equal to 0. So therefore, from this equation gives us A is equal to B. And now this equation gives us A plus C. Now here we have A plus C. So these two equations imply. Now we use this A plus C is equal to 1 here. So this gives us 2B plus 1 is equal to 0. And this thing implies us B is equal to minus 1 by 2. But once we have B is equal to minus 1 by 2, and this equation implies us A is also equal to minus 1 by 2. Now the only thing that you require is the value of C. So that this value of C can be obtained from this equation. So then A plus C is equal to 1 implies C is equal to 1 plus 1 by 2, that is 3 by 2. So thus we have obtained what is our F2. So thus F2 of X, Y, Z. This now X is now AX. This is actually equal to AX plus BY plus CZ. But now A is equal to minus 1 by 2x. Now B is equal to, in fact, again 1 by 2 y, and C is equal to 3 by 2. So this is 3 by 2 Z. So this is our value. This is our functional F2.
It's 3 o'clock.
And accordingly, we can now evaluate F3 of X again. Now F3, its action on V1 is 0. F3 of V2 is 0. And F3 of V3 is equal to 1. So this gives F3 of 1, 2, 1. Now again, this is equal to A plus 2B plus C. Now F3 of 1, 0, 1. This is equal to A plus C. And F3 of 1 minus 1, 0. This is equal to A minus B. Now by definition, this is 0, this is 0, and this is equal to 1. Now this equation gives us A is equal to minus C. Now if we put A plus C, in fact here we can use this equation. So in fact we should have done it like this. Now these two equations in combine give us, now since A plus C is equal to 0, so this implies 2B is equal to 0, and this equation gives us B is equal to 0. So here we are using this A plus C. This is equal to 0 from equation number 2, but here then we will get 2B equal to 0, and that means B is equal to 0. And once we have B is equal to 0, then this equation gives us A is equal to 1. And once we have A is equal to 1, then this equation gives us C is equal to minus 1. So thus, F3 of X, Y, Z, which was equal to AX plus BY plus cz. Now a is equal to 1, so this is x, b is equal to 0, and c is equal to minus 1, so this is x minus z. So therefore f1, f2, f3, these three mappings. The first one was, it was 1 by 2, 1 by 2, 3 by 2. So it is 1 by 2x plus 1 by 2y minus 1 by 2z. This was our f1. Now our f2, that is minus 1 by 2, minus 1 by 2, 3 by 2. So it is minus 1 by 2x minus 1 by 2y plus 3 by 2z. And now f3 is equal to x minus z. So this is the set f1, f2, f3, which actually forms the ordered basis of the dual space. So this is the set which is an ordered basis of. So therefore beta star is equal to f1, f2, f3 is the dual basis. And this is dual to the original basis beta. So we were given this basis beta, and now it is dual is obtained as beta star. Now we will assume that this beta star is given, and then we will find out the ordered basis beta. So that will be actually the reverse part of the same question. So now our actually second question is, so given beta star, which is equal to f1, f2, and f3, and containing these linear functionals x by 2 plus y by 2 minus z by 2, and minus x by 2 minus y by 2 plus 3z by 2 and x minus z. Now our question is to find the ordered basis beta. Find the ordered basis beta containing the vectors v1, v2, v3, whose dual is beta star. Whose dual is beta star. So we will start from this beta star and find out this beta. Now the solution. Again, we will use the definition of the linear functionals in terms of Kronecker delta function. So now here, f I of Vg, this is equal to delta Ig. So therefore, we have these equations. Now we have f1 of v1, that is 1, f2 of v1, that is 0, and f3 of v1, that's again equal to 0. So this will be our first equation. Now the second equation will accordingly be obtained from evaluating v2 under the three linear functions f1, f2, f3. So we have f1 of v2, by definition this is 0, f2 of v2, that is 1, and f3 of v2, that is equal to 0. And similarly, when evaluating the third vector v3 under these linear functionals, we obtain f1 of v3 is 0, f2 of v3 is equal to 0, and f3 of v3 is equal to 1. Now from these three equations, we have first, second, and third. From these three, we will evaluate the value of v1, and value of v1 can be obtained from this first, and value of exact ordered three tuple can be obtained, v2 can be obtained from second, and this v3 can be obtained from third. So now we will do them one by one. So now let v1 is equal to sum u v w. Then by definition, then f1 of v1 is 1, f1 of v2, sorry, f2 of v1, then f2 of v1, that is 0, and f3 of v1, that's again equal to 0. But by now we know what is the exact, what are these linear functionals, f1, f2, and f3. Okay, now our f1 is equal to x by 2, y by 2, minus z by 2. So therefore, this implies now f1 of v1. So now this v1 is equal, so that is f1 of u v w. This is 1, f2 of u v w. This is equal to 0, and f3 of u v w is equal to 0. Now f1 is equal to x by 2 plus y by 2 minus z by 2. So this implies u by 2 plus v by 2 minus w by 2 is equal to 1. And second equation is minus u by 2 minus v by 2 plus 3w by 2. This is equal to 0. And third is x minus z, that is u minus w. This is equal to 0. So now this thing implies multiplying both sides by 2. This gives us u plus v minus w is equal to 2. And this equation implies us minus u minus v plus 3w. This is equal to 0. And this equation is same as u minus w is equal to 0. We have to evaluate the values of u, v, and w so that we can find out this v1 equal to u, v, w. Now these two equations together give us these two. Now adding these two, we get 2w is equal to 2. So these two give us w is equal to 1. So once we have w is equal to 1, and from this equation, we will immediately get u is equal to 1. Now once we have u is equal to 1 and w equal to 1, and from this equation, then we will get v is equal to 2. So therefore, so from these two equations, first we will get w equal to 1. Now here, this equation gives us u equal to w, so u is also equal to 1. But then when we substitute u equal to 1 and w equal to 1, 1 and 1 gets cancelled, we will get v equal to 2. So therefore, v1, this equal to u is 1, w, u, v is equal to 2, and w is equal to 1. So in fact, if we look at our given ordered basis, so this was our first vector, v1, 1, 2, 1. And now we have obtained this 1, 2, 1 from the dual basis. Similarly, we can obtain the second vector, v2. Now, next, to find v2, let, again, v2 is equal to some u, v, w. Then we have f1 of u, v, w is 0, f2 of u, v, w is equal to 1, and f3 of u, v, w, this again equal to 0, because this is how we define these linear functionals, because fi of vj is equal to delta ij, the Kronecker delta function. So now this equation implies us, now this is u by 2 plus v by 2 minus w by 2 is equal to 0. The second equation gives us minus u by 2 minus v by 2 plus 3w by 2 is equal to 1. And the third equation gives us u minus w is equal to 0. Now this one implies u plus v minus w is 0. This one implies minus u minus v plus 3w is equal to 2. And this one gives us back u minus v, w is equal to 0. Now u minus w is equal to 0. So therefore, when we use this u minus w equal to 0 from this third equation here, this equation then implies us v is equal to 0. So let's write the steps properly. Let's call these equations as this equation number 1. This is equation number 2nd. And let's call this as equation number 3rd. Then using then 3rd and 1st give us v is equal to 0. Okay, when we have v is equal to 0, then using v equal to 0 here, then this equation implies us minus u plus 3w is equal to 2. And in fact, here we have u is equal to w. So then this implies, now using u equal to w, now using u equal to w here, we get minus w plus 3w equal to 2, and this implies w is equal to 1. But u is equal to w, so therefore this gives u is also equal to 1. So therefore, thus v2 is equal to u v w. Now u is equal to 1, v is equal to 1, v is equal to 0, and w is equal to 1. So the second coordinate, second v2, we obtain it as 1, 0, 1, which is here. In the similar fashion, we can obtain the last coordinate, v3. So now we will assume this v3 to be equal to uvw, and then evaluate these equations. Then f1 of uvw will be 0, f1 of v3 is 0, f2 of v3 is 0, and f3 of v3 will be equal to 1. Now lastly, let v3 is equal to u vw. Then f1 of v3 is 0, f2 of v3 is 0, and f3 of v3 is equal to 1. Now, using the value of v3 and using the functions f1, f2, and f3, we get u by 2 plus v by 2 minus w by 2 is equal to 0. The second equation gives us, second linear function gives us minus u by 2 minus v by 2 plus 3w by 2 is equal to 0. And the third one gives us u minus w is equal to 1. So from this gives, now multiplying the first and second equation by 2 on both sides, the first equation gives us u plus v minus w is 0. The second equation is minus u minus v plus 3w is equal to 0. And the third equation gives us u minus w is equal to 1. Now adding these two equations, u gets cancelled with minus u, v gets cancelled with minus v, 3w minus w is 2w. Adding these two equations gives us w is equal to 0. Once we have w equal to 0, then this one gives us u is equal to 1. Now using w equal to 0 here, u equal to 1 here, we get v equal to minus 1. So this implies then v is equal to minus 1. So thus v3 is equal to u v w. Now u is equal to 1, v is equal to minus 1, and w is equal to 0. So this was our third coordinate vector, v3 in the ordered basis beta. So thus beta is equal to v1, v2, v3, and this is equal to 1, 2, 1, 1, 0, 1, and 1 minus 1, 0. And now we have obtained this beta by using the ordered basis beta star. So let's stop now, and today we will do only this much.